should be live, in which case if I go to the channel,
Yep.
let me just drag the chat out of this. Interesting. Yep. Live control room. I need the link. God damn it.
Which link?
Link to the video. Never mind. Okay. Right. I need the chat to pop out. Right. All I need to do now is check if the audio is alright.
Testing 1 2 3.
Not now. Wait. Give me a moment. Let this chat be here. I will go quickly listen in from here. Keep talking.
Testing 1 2 3. How is the voice?
I need to find out a better way to do this. I need to change this title as well.
Kitty.
Save. Concurrent viewers 1. Share. Here's the URL.
Where? Oh, acha.
Let's watch it here.
Check from the beginning, you will get the
Yeah, the audio is cool.
audio is good. Okay.
Also, it's the latency is low.
Okay.
Cool. Okay.
Close the multiple tabs there.
Right. Only part that is challenging a little bit is that today we are going with the same internet source. So
Yeah, I know that.
Let's see if there is any lag because of that. So we are using not a secondary internet source only for the streaming, which we have done last couple of times, which worked out really well, to be honest. But today we are going straight up with the same source. We didn't get enough time to set those things up. So so today we are going to work with this laptop power battery pack and get the batteries out of this individual cells and prepare them for DIY projects. So just to set the context, the laptop that we have shown a couple of weeks back, this is from that laptop. This battery pack is from that laptop. How about this? Right. I should now move on to this.
Yeah.
This looks fine. So this is a battery pack from Momita's laptop that we had to tear down because it had suffered some power circuit damage. Even though the power circuit was damaged, the battery itself should be absolutely fine without any problem. That's what we think. And from the outside looks of it, seems like the load switch of this battery power circuit was the one that blew up and it blocked this thing from suffering any kind of damage. So there is no issue that is like at least visual inspection or like structural infection, battery puffing up, like nothing of that happened. So all the cells should be really usable essentially. Just to show the rating of the cells, like let me find out where it is. Yeah, here. So right, as we can see, it's a 7.68 volt, means two cells in parallel series, and typical capacity is 7820. So that means also two cells in parallel.
Yeah, I can see that from if you
so
turn
it's
it
2
over.
by 2 essentially.
Yeah,
It's 2 by 2, right? So 1 2 1 2. So basically 2 of them are in parallel and then those two banks are in series. So that's how it is set up, and overall capacity is 60 watt hour, which is pretty good. And these cells would be really high quality cells if we can salvage them properly. However, word of caution, this is very highly dangerous, and this LiPo cell, this is highly flammable. We have equipment to, like, in case of a fire which we are not expecting, I intend to handle it with care, but in case of that we have a way to suppress the fire. So yeah, if you are attempting something like this, make sure not to puncture the batteries even accidentally, or try to cut the cables with one knife, where when you're cutting it, the plus and minus gets momentarily short circuited because it's the same metal connecting both of them. So those kind of, like, it doesn't occur to you until it happens to you. So those kind of situations are really, like,
I remember.
Yeah, that can happen, and that can be really really dangerous. And it is very easily avoided if you know what are the do's and don'ts. And hopefully, so Momita is here. She works as a, like, reality check for me, like things that I end up saying or words that I end up using that may needs further explanation. It helps that she asks me the question, okay, what do you mean by that, kind of way, and I get a chance to ask more.
Noob check.
It's a normal people check. Like, most people are not, their day is not, does not start or end with salvaging batteries and lipo cells, etc. Right. So far, any question? Anything you like?
No,
you
nothing.
think?
So, how are you going to proceed? Because I see this, and
Yeah. So this is the battery connector, which is, like, a lot of conclusion you can draw out of this. Like, I think we need to get the, like, because of the motherboard, I put the thing a little higher up. I think we can, like, get it a little bit down now. This makes sense. Yeah, so this is better. So this connector is proprietary to Lenovo.
okay.
Like, this is not any kind of standard compliant connector. Lenovo made it the way it made sense to them. However, we can see a couple of things from here. One, the red wires conventionally are power, black ones are conventionally the ground. There is also 4 different wires in here,
Yeah.
and those are for communicating with the chip, as in communicating with the power circuit. Because even though the charging and discharging as in protection circuit is inside here, whether to charge, when to charge, how much to charge it with, etc., those kind of things, when to shut it off, like when you're putting the computer to sleep, etc., those kind of things, when to put it in low power mode, those information needs to come from somewhere else, external. And that's the SM bus. It's a system management bus interface, which is a form of I2C, like IC to IC protocol.
So that is inside here.
Yeah, so here you will find a battery management system, BMS.
Okay.
And BMS will have a couple of things. First, the entire, that a chip to talk to the external chip to basically know, like, and also count how many power cycles are there, like how many times you have charged it or discharge it. And if the manufacturer said that, okay, this is the maximum number of charging discharging cycle, after that, like, declare the battery is bad and then stop working. Those kind of things are also possible. So that is something that will be there. Aside from that, there will also be how much to charge it, the current width, how to control the charging current, when to cut it off, and in, like, individual cells being cut off in that point. Like, there will be battery tabs for individual cells to be connected, their positives and negatives to be connected, so that the controller can control which one needs which kind of as in.
But this is wrapped so well.
This
like,
is wrapped.
How to open this?
So first of all, I'm not going to cut any of these unless I think that is absolutely necessary, right?
Okay.
So my understanding here is, if we go by unwrapping the this black covering, which is, yeah, it's not thermal, it's just protective sheath, which is making it also insulating it from the outside. So if we can carefully, gently, like, pull it off like this, we can already start seeing those battery packs. Make sure that's not to structurally, like, do anything to the batteries.
Press it.
Yeah.
Okay.
So I'm making sure to distribute the pressure so that none of the section of the batteries are suffering any kind of structural damage. That is very much essential. Like you can, it's like even if there will be no fire or anything, you can reduce battery's capacity by bending it or something.
You want me to hold?
Yeah, it will be good if you hold on this side so that I can make sure to pull it properly. So they just use glues, which is most often the standard practice. Although I don't like it, this is cheapest and easiest option than any other alternative, so I understand. Also note the way I am pulling it. I am not pulling it upside, I am pulling it side by, so that this thing is not coming out.
Yeah.
So that is most important. You don't want to structurally damage that, because there are lots of ways to structurally damage the battery cells. They are not meant to be disassembled. Like they were not created, packed in this format so that somebody will have a nicer time disassembling it. They made it in a way that makes more sense for them to put it together and operate in a normal operating condition. This is what we are doing is not really an intended use case. So be very extra cautious about what you're doing, which is unfortunate. I think we should have a proper industry for recycling these things, e-waste, because there's a lot of things, like most of the time, one of the thousands of components that actually breaks. For example, in your component,
Okay, do battery gets bad? I mean,
batteries can get bad. Sometimes for some people, battery is the one that got bad. But even then, the SoC and RAM and everything else will also be thrown out. The altogether thing, they will consider the whole thing does not work. I don't really have a proper use for this plastic, so I'm gonna practically throw it out. If you have a place where you can utilize it, it's actually really good adhesive, one-sided adhesive plastic. You can insulate something with it. So now it's time for us to gradually pry open the these tabs. It's also glued, so I'll have to be careful. Although I have all the cutting solutions, I am avoiding it until it's absolutely necessary or needed. All right. So, right. I think if we can just, we have
to go from here.
We have to like go to the. Is it visible?
It is.
I don't know.
The yellow.
So what I'm trying to do, I'm going to wedge in from the outside like this, avoiding the battery altogether, and try to basically pick out, like find a place where I can pull it from. Right. Now that I have that, I can use my fingernails to pull the tab out. Maybe this.
Yeah. Oh, it got stuck again.
Right, so we were able to pull it out without any kind of structural damage to the thing, and we have to just repeat this process like for the whole thing. The good news is that it's actually, if you can wedge in from one side, gradually it comes off and takes off a little bit of more from the other side as well. So yeah, gradually, bit by bit, you have to strip it off. The reason I took that like initial photo here, because this is really important information. Can you remember it? Or otherwise we'll have to watch the video again. So what is half of 7820? That's 3910. It's like roughly 4000 milliamp hour cells each one, individual one.
Yes, it's a laptop battery. Somebody's asking.
Yes, it's a laptop battery. It's the same cell that if you have attended the previous 2 weeks ago on our stream, we showed the broken laptop that I tried to fix and that had power circuit damage. So the battery pack was not bad, so we are trying to salvage the batteries from that battery laptop's battery pack. Momita is asking me questions around that. So, and if you have any question, feel free to ask. We just explain.
What is this?
So this is the other side of that battery, this cell.
Oh, okay.
Other end of this cell.
So it's like a frame and then wrapped in.
It's wrapped into both the sides.
Both the sides.
One good thing about YouTube is that you can go back and watch the part that you missed. Like it's live stream, but you can do that, and then you can play it at 1.5x or 2x and catch back up. I do that all the time with most of the time one show, like Linus Tech Tips one show. When I start, by the time they probably already have started and done like half an hour of chatting. So I start and I play it at 2x, and in another half an hour I basically get caught up with the actual live.
What is this yellow part? Yellow thing?
Yellow part is the Kapton tape, essentially. Like, so this whole thing is held together for making it structurally stronger. You put a Kapton tape. Kapton tape is like, it's a polyamide tape. It's a bit of a heat resistant, fire resistant tape. It's like cellophane tape, but has some better other properties than cellophane tape. And
so this is not a single cell. I mean, it has multiple. This battery. It has multiple things inside which is stuck together.
Of course, like even the cells are made off of some other things. None of it, this is one particular element of in nature. This is a combinational thing. In fact, even the even if you go down deeper down, like the cathodes and anodes and the what do you call it, the dielectric in between and all these things, those things are all combinational. Like you are using multiple different chemistry together to get to what you want, the properties that you need. Sometimes you're working towards faster charging, sometimes you're working towards more capacity, and those are the kind of things. Okay, we need to, I think better option is for me to cut it open here so that the plastic covering can protect me from reaching the battery.
Use this. Okay.
No, this is better. That one is way too sharp for my taste. I was trying to watch your high quality DIY mind video but couldn't complete it. Great channel, Dada. Hey, thanks, man. Yeah, the glue makes it really hard for basically you working with it.
That's
Previously,
why they make it like this.
No, previously it used to be like plastic casing. Even the MacBooks and all, they used to have plastic casings. And you could screw, like unscrew the thing and it will open up. Problem with that is, that will be not as thin as this, right? Like every like fraction of millimeters matter. So a plastic casing would increase the thickness, and that is not good. So they figured out ways to reduce the thickness and make it less repairable. Not really repairable. Like they would say that okay, you should just go ahead and change the whole battery pack if you have any issue. So from repairability side, they would just go with that excuse. However, it still increases the e-waste.
Yeah, unless until people can reuse the batteries. I want to see what is inside this.
Inside this,
Yeah.
I have to open this part then for that matter. I would want to, but
No.
this thing is I have to go from step by
Yes,
step,
you
right? Might make more sense for me to go from the middle and try to split it open from the two sides. It will be faster, but it will also be riskier. So I'm
No,
not
no,
I'm not taking
it's
chance.
fine.
I'm basically like, it's okay if it takes longer, and if it turns really boring or something, then I'll probably do it afterwards. But for the timing, this is what is expected. I don't want to create a false expectation of like this is super fun and you can do it very easily. It's not that. Like, it is dangerous, it's not very fun, it needs a lot of patience, and sorry.
Slowly, this thing was.
Yeah, it requires a lot of patience, and basically you have to pry it open step by step gradually. It's like eating a very complicated fruit.
Beyond.
What's the most complicated fruit you have eaten? That takes a lot of processing time. Like, you have to prepare the fruit.
Pomegranate.
Pomegranate is one of those. Is it too unsafe to use a knife or less sharp pry tool? I mean, if you're confident about it, go for it. However, the risk, like, you just have to make that mistake once. Like, you do it well 100 times, doesn't matter. You just have to make the mistake once, and that is enough to ruin basically the whole thing that you're trying to do. Which is why, like, it doesn't even have to be like something that you are trying to do. If your hand gets shaken and you like accidentally poke it somewhere, it can still do the same kind of damage. So I'm trying to avoid knives and pry tools, etc. Like, I have all those things if I need, but I'm trying not to use them as much as possible. Jambura, I don't know what they call it. That's called a grapefruit, not the grape. Grapes are different. Grapefruit is jambura, I think, if I'm not mistaken. Can do a quick Google search if jambura is grapefruit, or Google Translate. That will work as well. Jambura. Yeah, those kind of fruits. Like, it takes a lot of processing time. What is ata? The custard apple.
Custard apple.
Yeah. Custard apple.
Custard apple.
Okay, we are making progress here, guys. We are making progress. Is the first initial part is the complicated part. Gradually, it gets easier.
So, what are this paper thing that is here? Why these are there?
They added it for structural support, I think.
It's exactly between these two.
Okay. All right. Now, এখানটাতে we can try. This is facing down. Okay. Yeah. The camera needs to be a little bit like this, I think. Otherwise, it's barely visible. I'm barely visible. Okay, patience. I will be patient. Like, those are easier to open up.
Yeah.
So gradually, we almost got it. Like, it's, as I said, like, initial part is the hardest. Gradually, as you go down the thing, it will be easier. So polymer cells, I haven't opened any, like, as many times. Most of the laptops that I have opened, like, so far, they had those lithium ion cells, like the 18650 cells, because those are the ones that are bad. Like polymer cell laptops are going bad now, like those ones that we have started buying back in like 15, 16 and all those. Those are the ones going bad now. So far, where we have been opening those 18650 cells. Yeah. The previous, like, not Li-Po, those are Li-ion, lithium ion battery cells, right? So I'm
What are the cells that is there in mobile?
LiPo, but it's a similar kind. However, they are put together in a different manner. Not like this, unlike this. The casing part of
Yeah.
in mobile you're not having usually like until recently you didn't have too many cells. It's just one
Yeah.
cell is one battery. Multiple cells, that is a concept when you need faster charging. That is something that you need when you need faster charging. So it is being introduced now, like new OnePlus 13
Yeah.
has a really like getting rave reviews. It actually has done some really is like this would have been a mistake.
Yeah.
I need to be more careful, even though I'm preaching it, I'm not practicing it well enough. So they're getting rave reviews, and they have done pretty good job at like battery charging the circuit. So it has two batteries.
It has two batteries.
Two cells, not two batteries, one battery, two cells, because it needs to have faster charging. Even wireless charging is 50 watts or something.
This was 60 watt.
This is 60 watt hour. It's not.
Watt hour.
I don't think it's charging at the 16 watt hour, because the charger itself was 45 watt charger, so it cannot even provide 60 watt power.
Yeah.
No, I'm using going through that casing.
Yes.
So this should not at all be problematic. Okay.
No. Use that.
No, this is fine. This is fine. I'm just trying to wedge out the plastic from here. Right. Yeah. All right. This side is pretty much done practically. All right. That was such a journey. It's not over yet. We have these small ones. Chemistry wise and like basically for performance wise, those mobile batteries and these batteries are same or similar. However, they are organized in a different manner for laptops.
CDs and parallel.
Yeah. And so what I was trying to tell you is that that would be a problem. These glues are basically pulling out the felt from here. Okay.
It's opening up.
Yeah, this is coming loose, so this is already like opened up, like you can see the other side from here. So this is loose. This is not glued in here, which is a good news. I like that. Would have been a real nightmare if it was glued as well. So okay, cool. No, I need to do the same thing, like right. Yikes.
No, you have to pull it.
Can you try with your fingernails maybe?
Don't.
Let me try and open this part up in that case. So the 18650 cells used to have their plastic casing. It was really difficult. Don't pull it like that. Like you have to pull it like a 80 degree, 180 degree on the corner. So they used to have plastic casing. It was real hard to get into that. But once you break the plastic casing, it basically the whole thing comes together out. There's no glues and stuff. It used to be a silicone adhesive, a little bit of. That's it. So structurally, this is more complicated as a build.
But it's very stable also.
Yeah, it is also stable. Like that is true. Okay, one last thing. Tab that is here. Let me open this up. So prying the first part takes a lot of time, and then prying the last part takes a lot of time. The middle section is pretty easy. When the bulb, somebody's phone is ringing. Okay. Uh-oh. Can you manage this?
Yeah.
Maybe throw it out.
It's very thin.
Do we have our calipers here? No. I wanted to measure exactly how thin it is. Like 6 millimeter, I guess.
No, it's not here. Here it is, little bit.
Yeah, that's fine. Okay, we should be able to pull it out. This is a real gaming patience. Alright, now two more times, I guess, and we'll be in. Whew.
They do not want us to recycle this.
Yeah.
Absolutely.
I mean, like, it's not that they are trying to be evil or anything. Like, the government's rules, regulations, the way people post videos about any time a battery cell burns up because they want more likes and shares, and makes it very, it's like an asymmetric playground. If even one out of millions of devices that you're making ever catches fire, you are treated really poorly for bad engineering. So what do? They do over engineering of, like, okay, you're absolutely not allowed, like, I'm not going to make it in a way that is even an option or a choice or a problem, even if you're really careful, even if you want to do it knowing what you're doing. So that makes the whole problem.
Okay, there is a question there.
Yeah. Are those 4 cells? Yes, those are 4 cells. 4 individual LiPo cells, each one 3910 milliamp hour, according to the spec, which I will later on, like, charge, discharge, like, cycle them like 1 or 2 times to figure out exactly how much power they still hold. And I'm not expecting any kind of bad cells. These are not bad cells, like, these are actually good cells. The laptop has other problem in the power circuit, but battery part was really, like, there was no issues with that. So I'm expecting the batteries to work really well. There is no puffing up or any other kind of structural disintegrity. The batteries should work just fine. Right.
Yes.
Right. So now that we can see, this cells are basically coming off. Yeah, but I'm not gonna do that first. I'm going to try and open this in middle section, which is holding the.
Oh.
Uh-oh.
It's coming out.
Oh, okay. No, that's actually not bad at all. Like, if it comes out like that, that's good.
Is there any connector with the battery to that place? I mean, should open it and see first before pulling it.
Where the connector? Of course, there is connector, but I'm trying to see the connector is from this side or that side. Also, we have to be really careful about not breaking the battery tabs, because that will make the battery tabs unusable. So I need to find out exactly where the leverage point is to open up the cell.
Is there any screw or something?
Yeah, this plastic needs to be actually broken from this side. But I cannot use the batteries as the leverage point for breaking this because
Can you cut it? I mean, the frame.
no. Yeah, so I have to cut the frame, but not while the batteries are still
Wait. You
intact like
remove
this.
that then.
Is it visible? Okay. This is the one last tab. Alright, so the first quest is done. Let me take a breather and then figure it out. Let me switch the... Oh, this looks like those...
Don't share it.
Looks like those ornithopters from Dune. The ornithopter wings. Alright, give me a moment. Let's take a breather. Alright. Now, the entire electronics and all these things we were talking about is at the middle, at the central part, this section. Now,
Seems like there's here something and here.
no, those are tab. There's no screw. Like, I can show it to the camera. Let's go back to the cam. Here, do we have enough light? Like,
No.
wait.
Wait.
Wait. Something like this. Okay, right. So there is no screw. It's just hot press tab. Like the tab is hot pressed to like fit with each other.
Got it.
Right. So the only way is to open the two shells from both the sides. Now that would be a little bit tricky. I am assuming this side should be, I should be able to pry open, and given that the battery ends here, my best bet is to pry it from the middle. I need a flat head screw, as in a screwdriver.
See, you have here or wait.
Let me see. This is a really thin bit. Let me put these things aside for a bit because I need more working surface. What I'm doing is that I'm prying open from one edge and trying to
Break it.
wedge my way in. If I can find a weak spot here, then I can apply more pressure and get inside from there.
Yeah.
Yep.
Seems like it opened.
Nice. So this is a plastic tab that is opening up. Okay, cool, awesome. This is the best case scenario. Nice. We got it, chat. That was easy. It wasn't. Now, actually, before I go any further, I should be able to explain most of the things that I wanted to explain from here itself.
Seems like this is also a power battery management. This is also a...
The whole board is a battery management system.
Okay.
So this whole thing, this is a PCB, that is battery management system, BMS. This is a power, this is ground, this is communication lines, mostly I2C. That's basically SM bus if you need more details about it. Anybody watching this? And hey Pritham, so I'm really happy about it. So if you're looking for like what is it this interface is about, it's called SM bus. It's somewhat standardized, like as in to the point pretty much all the power service ACPI power service devices work with that communication protocol is SM bus. Now this is the main IC it looks like, start of the show, which takes in all the information and tells the individual components here how to behave. For example, the MOSFETs to open, which is like the drain MOSFETs, so as in whether or not the batteries should be connected. So if it detects a short circuit or something, it will say that, okay, I stop working, no power to you.
Okay.
So basically cutting off the power, etc. How to behave, this is the guardian in the room.
So MOSFET tells whether there is a short circuit?
No, the controller tells the MOSFET. So you can imagine the controller as the manager and the MOSFETs are the employees, like the individual contributors who are doing the individual things. So basically they are one with the lever. One with the lever, if you tell that, okay, hey, cut off that power, they just pull the lever and the power is cut. In that way. So basically MOSFETs are nothing but switch, but they're logic control switch. They're not physically controlled switch. All it takes basically some voltage to go up or down, and that's a signal to the MOSFET to do some certain thing. If for some MOSFET it's like you pull the power up and they open the gate, that opens the gate and then the power goes from one point to another.
So the capacitor and resistors are doing, and then MOSFET, and then the IC.
Capacitors and resistors are there with a stable, static, predictable property.
Okay.
Like they do one thing and one thing well. Like resistors resist, they stop or slow down the flow of the current. You can have multiple different uses of this. Like these are not one purpose devices. The property is stable, but you can use it for various different reasons. Like sometimes you need, like people will tell you that, okay, put a resistor in series with a LED light that you're trying to light, because what it is doing is limiting the current that can flow through the circuit, so that the LED doesn't burn up. LED is a silicon device which have no like linearity. It will, if you just increase the voltage, it will shoot up the current and practically work like a short circuit and then burn itself up in the process. Resistor stops it from happening. Now you can use that property for multiple different reasons. Sometimes you use a very small value resistor in that, as in series, and measure the drop in by the side to determine how much current is flowing through. It's called shunt resistor.
Okay.
Sometimes there's a current limiting resistor. Sometimes they're like a configuration resistor where you're charging a capacitor at a certain rate or some other kind of thing, where the resistor makes sure the voltage doesn't shoot up, instead it slowly rises. And that brings me nicely to the capacitors. Capacitors are basically like, you can consider them as small batteries right in front of the thing where the power management is needed. So instead of the power being supplied from the main sources all the time for every small little thing, the capacitors are the ones that are staying charged. Their job is to stay charged and provide a stable static voltage to the device they're connected to. So
then there is MOSFET.
Yeah, so capacitors, resistors and inductors, those are called passive components. Their property stays the same regardless of the voltage or current. Like they're linear devices. It does matter like how much, if you're going with the AC current, like as in something that is switching on and off, and at how much frequency, then their behavior changes a little bit, and that's a different story altogether. But for the most part, they stay. Their behavior do not change. You can use them as one thing that does one thing for that particular circuit. MOSFETs or diodes or this like a combinational circuit that is like ICs, integrated circuits, they don't have one particular behavior. They're logic driven circuits. Like if you do this, then I'll do that. If you increase the voltage here, then I will open the gate. But that voltage has to be more than 2.5 volt for me to actually open the gate properly.
Achha.
Otherwise, I'll half open the gate.
Okay.
So those kind of things, like
that I mean like that I will half open or I will full open, that is done by IC.
So no, now do you want it to be half opened or do you want it to be full opened? If you want it to be half opened, then you design a circuit like that. You operate it in that linear region where it behaves almost like a resistor. And then if you were like, no, I want to use it as a power circuit where it's like a switch.
Yes or no, yeah.
In that case, doesn't behave like a resistor, it behaves like a short circuit.
Okay.
So the MOSFET's curve goes like this and then this. this and then this. This is the knee region. So anyways, that's a much deeper discussion, but the point here is it's not linear. The behavior doesn't stay linear. How much voltage is being applied at the gate and stuff, that changes the behavior and the current output. Usually you would choose like when you're using it as a switch, okay, I need a plier to to hold that capacitor, because it's, so if you can see here, each one of the tabs, each one of the, these are the battery
one
tabs,
or
right?
two?
Just one, but the blue one.
Okay.
Give me, let's put it here. Let me show one more thing. So these are the battery tabs, 1 2 3 4 5 6 7 8, and this is also pretty much marked which one is which and how does it need to be.
This is one.
Right, so, and this is this point that you see here, the 6 points, those are very industrial grade welding, like spot welding, as it seems. So they just spot welded the device with the PCB here. There is no good way for me to open it up aside from
what is below this thing, this metal?
this another metal surface. So basically spot welding, what you're doing is spot welding, you're running a very high amount of current through this so that it gets fused. Literally the metal melts down.
Like metal with metal.
Yes, metal melts down and fuses with each other and becomes practically one thing. So the connection is not a soldering or anything, it's basically like the same thing. I think I can pull it out, but if I can't, I'll use the...
Yes, I think you can. It's not...
I don't know whether I can show it to the camera properly. Okay.
Yeah,
yes, I'm able to pull it out. Let me try the second time and then I'll show it to the camera. Okay, we got it. So with very minimal damage.
Go a little below.
No, it'll be fine. So as you can see, the part that came out are those 8 tabs, the anode and cathode terminals of the cells. Yes, 4 of those are anodes, 4 of those are cathodes. Which one is which, we'll have to check. But from here, as you can see, this one has a black marker here, means, as in I would assume this one is the cathode and this one is anode, right? So, but I'll bring out my multimeter and check in a moment. What I'm trying to show here is that the part that you see the metal is missing, that's the part where it was welded, and the weld is so strong that practically it stayed with the board there, and it tore up. So okay, that's one cell. Now probably it will be safer. Chat, should I like show that to the camera? Let me try. I don't know exactly how well it will go, but
do you want me to hold?
Yeah, can you hold this from the, so that I don't have to worry about it falling down?
No, yeah.
So I am basically gonna pull it out like this and then pry the tab open with finger.
Ow. It's literally making noise. Tuck, tuck, tuck.
Yes, it came out even more nicely, even though it's on camera. Like I'm having really hard time pulling it out, but it's coming out nicely. Okay, all right. So this is how it came out. We got that on camera this time. Nice. By the way, this also has a board here. You cannot see it. This battery, this is not where it ends. The protection of the battery, individual cell, is also there. Here, there's a small PCB that has the battery is cut off and all these things.
Yeah, it is there.
So if something goes wrong and this board cannot catch it, and the battery is facing a short circuit or something like that, overcurrent, overload, over voltage protection, it will still cut off the power right from here. It will just stop responding, and this system will say that one battery has gone bad, like it's not responding anymore, and do what is necessary to do, or maybe it has failed. This makes sure that it doesn't catch fire or like end up short circuiting or something.
So they do take care while...
Oh wait, you have to, like those are not something that is negotiable. If you're making a device for people, and those are the things, like that's the thing that you can get away with when you're making a DIY device. Some of the things that I'm making for myself, I know my limit and my use case and all things. when you're making for a general population, people will subject it to lots of different kinds of abuses and like use cases. They think that is normal. Like for example, somebody cutting the tabs with a knife, both the tabs like a red and blue, like red and black wire, they're cutting it with a knife. They're probably not thinking that much. I shouldn't be doing that. The moment you cut it, that metal of the cutter is touching both the red and black wire. It's short circuited at the moment. That can catch fire or at least cause serious damage. And those are things people end up doing, and engineers have to take care that that does not end up ruining the whole device. Because even if it's their problem, they will end up wasting. Yeah, you can take this away. We have been able to take the frame away. So even though the challenge is on the issue is on the user's end, and we can prove that like you have done this, and they will end up taking the customer support time and that's cost to the company. So when you're designing stuff, you have to make sure that you're mitigating those kind of cost to the company. Oh yes, you have to be really careful with the tabs. If it was
it's coming out.
it's really difficult to hold this. Okay, okay, I'll do it like this.
Are you fine? Okay. Do I need to hold?
No.
Okay.
This one is really strong for some reason. Oh my god. I didn't break it, right?
No.
It's fine. Alright. I mean, there's one layer down. Like, even if it ends up breaking, I can just open up the battery cells, that BMS protection, and go one level down to find out the actual cells stuff. But I don't want to do that. I want to use the cells as is, as much practically possible, and tap, like add wire, like cables to the ends so that they can be used as is. The last one.
There is a wire. What is that wire?
That one is for, let me tell you after I open this up. Okay?
Open it carefully. Don't tear that, I guess.
It doesn't really matter. This one does not matter. I can take it out. It has a small bead-like thing at the top. It is glued down. Okay. This makes it a little bit difficult to handle.
Oh
my god. Yikes.
Okay. Now tell me, what is this?
This is thermal probe. So it's checking if so basically resistance of this thing goes down if the temperature goes up. So by that you can tell if the temperature of the battery cell is going too much higher up, so that you should limit the charging current or etc. Right. So you put that from here to wherever you put this thing, the top head, wherever you expect the temperature to rise. So that's why they put it like next to the battery tab. So this is the BMS, really well designed. I actually like it. The design, I love it. Okay, yeah.
So why only for one battery?
Because you don't need to place it multiple times. If something is heating up, you will know from one place itself.
Okay.
Right. It will like that. Right. So we have now all the 4 cells and the battery pack. Can you put these things out there? Like, if I don't even need this, even these ones I don't need anymore. They go the same place. Okay, let me arrange them up in a better manner. And then I need the multimeter. Can you bring the multimeter, please?
Yeah.
Right. Okay. Right. Let's take a bit of a breather. So intense. I need a little bit of coffee. Hi chat, what's up? Who's watching?
See.
No, go to the other. No, not here, not here. Leave it, it doesn't matter. Yeah. Right, so that went pretty smooth compared to how, like, how many millions of options there are. Yeah, so you can even put the fire. Like, okay, don't do it now. Like, it's still like we're not over with it yet. So I'll need to.
So what was that black thing you were talking about? There is something which is this side. And
Yeah, so the black is the cathode and the not black one is the anode, presumably. Now let's measure the voltage first, quickly. And here's what the prediction. One thing I will say, that sometimes you measure the voltage and one of those cells will be really low. Usually that's the first cell.
Okay.
That is the cell that is being used for even running the BMS.
Oh, okay.
So if the BMS is being run with that cell for a long time and the battery, like it wasn't charged for a long duration, there is a chance that that cell would seem like it has drained or it's bad cell. Not necessarily the case. It might just be the first cell, which usually is the one that is used for that purpose, or it can be last cell, depending on how the circuit is created. The point is, just because one cell seems a little bit off the norm for the battery, the voltage check, does not mean that it's necessarily bad. Now I'll go to measure the voltage. Seems like all these ones are negatives on the side and the other one is positive. So let's see. I am expecting to get somewhere around 3 volt to 3.6 volt. 3.2,
3.2.
3.23, 3.2, 3.23. So these are really well done batteries, and
all are same
yeah.
charge.
No, I ensured that they are discharged a proper amount before I open it up, because lesser power you have in here, lesser chance of fire happening, even if you end up. So if you're opening a battery packs or something, make sure to discharge the thing, not like deep discharge, just go up to the 3 volt or something like that, which is practically speaking, from in battery's term, 10% charge. When you go to 3 volt, it will still give you power up till like 2.8 volt or something, but that is the place. Like, you should not, working with LiPo batteries, LiPo cells, avoid both the last and first 20%. Do not deep discharge, do not deep charge. Yeah, so that's one of the things that I wanted to talk about. Yeah, now is probably a good time to talk about that part. So maybe we should like create a short video on the breaker space.
About battery.
Yeah, short about, just for example, tech tips, like those kind of tips, like you may or may not know, but it helps to, as in, if it comes from a source where the resources are given to you, like this is the reason why. It's not just blindly like do this or don't do that. So I was thinking, like, so we started the Instagram channel, Breakerspace Instagram channel. Yeah, so we started Breakerspace Instagram channel. Go look for it, follow, give it a follow. It's just very new. I haven't posted much there. I'm thinking about what to post there.
We can post
these kind of small
tidbits.
Yeah. For example, one like tip is if you want your battery to last really long, and the battery is not having that charge cycle counter as the cutoff period, but actual battery's charge and discharge level, which is the newer and better ways to like decide whether the battery is good. So in that sense, what you can do not let the battery go below 20% charge, and preferably do not charge it above 80% charge.
As much as possible. 20%.
Yeah, like leave both the 20% on the side, and your battery will work. You can use the battery 10x more times than otherwise you would if you try to charge it fully or drain it fully. The newer MacBooks and many other devices like OnePlus and all, they have those things, kind of software built in, like they will say night optimized charge, and they'll charge it up to 80% and then
Yes.
really slow down the charge after
Yes.
that. So those kind of things that they don't want to. They cannot communicate with you all those extra details. Most people do not want to know, do not care to know. But if you can manage to do that, like if you're not carrying around the laptop all the time, just make sure your laptop is like 80% charged. And if you are sure that, okay, I'm going outside, I'm not bringing my power brick, but my laptop can support for the entire day and it will not go below 80%, which is true for most of the like MacBooks and stuff, like most of the laptops that we are using nowadays. So in those cases, it's absolutely fine for you to like do that and not try to charge it fully up to 100%. If you do that, it's not gonna be like twice or 5 times as good. It will be more than 10 times as good, because the reason that happens, the reason batteries go bad. So limit my phone's charging to 80%. Why is it advised to be? So, okay, yeah, that's what I was getting to. So when we charge the battery cells, right? What's happening? These lithium ions are going and being deposited on one end, and the electrons are going from the other end. Like, this is a rough way to understand this. So, and the deposit, when you created a like clean battery, no like as in a pristine new battery, this will be a small layers, like basically sedimentation of layers of lithium that will be built up when you're charging it, and when discharging it is just going down there and meeting up with the electron and becoming a normal thing. So in both the cases, it will be like a very clean, polished sediment where you can see the layer lines and stuff. But gradually over time, what happens when you do the deep charge and deep discharge? What happens? First, let's say deep discharge, right? When you're deep discharging, like you're going below 20%, you're like 10%, 5% charge. You cannot go to 0%. Most of the time, you're not going 0%. What happens? 5% charge means there is a little bit of like deposit here and there. Most of the thing, like most of the lithium has gone off that plate, like cathode anode plate, and some spots are still there, right? Now when you're charging it back, what's happening? The new lithium are going and being deposited on the existing spot instead of on a free spot.
Okay.
So when it's going and being deposited on the existing spot, what is happening? It's creating hills, like mountain ranges. Instead of spikes. Instead of, it is not spike yet, it's just mountain ranges, right? And the mountain ranges will grow and go up to like, if you are 80%, it will still be like separate enough from the other end that it will not be a problem. Now you keep on doing that, the difference between the highs and lows of the mountain range will go higher up. It will become like trench and like Himalayas and Mariana Trench, that kind of thing. And you keep on doing that, it will basically start becoming one of the hotspot that is like really like all that.
Is it because of that the mobile gets hot when you are charging? Even when you are charging, mobile gets hot sometimes.
So that's a very different reason. No, this is not the same thing. Okay. Even though if it is getting hot, the charging current will be slowed down, because when it's hot, the things are mobile, very mobile. So basically, it's easier for it to build up a small, like a higher, like structure, like a spike. That's when it becomes from mountain range to spike. And if it end up becoming a spike, it has a way to, like, it has a at some certain point in time, it will just reach the other end. And if you end up connecting so basically internal short circuit, the anode and cathode.
Okay, so if it is 20%, so there are lots of spots.
No, if you're at 20%, there are no spots. It's not depleted. If there's a small layer of...
Okay, there is a layer.
There's a layer. So when it's coming down, it can basically deposit anywhere. It's just close by. It's not getting pulled to... You can imagine those spots being kind of a magnet, where the current is higher. It is drawn towards that spot. The kind of like basically fish getting into the school.
It's like not one spot. If it's a layer, the whole thing
magnet,
and it can just stabilize and make space everywhere. Get distributed. Get
evenly distributed.
Yeah, okay.
Now, if you do that on the both end, right? Like you're not letting it getting depleted as much, and you're not letting it like getting like go higher up as much. Like so, in that case, this thing overall behaves very like a well-behaved kid.
Yeah, exactly.
Like there's no childhood trauma or anything. But more and more you do that less than 20% and more than 80% charging, it has those traumas and trauma markers, and basically it needs more therapy. Anyway, so that was the reason. So maybe we can basically explain the whole thing in a small short video, and then
So when the batteries get puffed up, is it because of that thing?
no. So you asked two questions, right? Let me answer both of you. So the reason battery is getting puffed up is because of so there is a gas that is being generated there. In normal 18650 cells, you will see on the anode side there are some couple of like holes that disperses the gas, like disperses the gas. It's not held inside, so it doesn't puff up.
Okay.
This is kind of a natural process when it happens. It does reduce the battery's capacity a little bit, but it's not that problematic. What the problem here is that when that happens to these cells, and some part of it is related to the uneven charging, that's when it happens more. There's no good way to like as in release that gas.
Exactly, it's all covered up.
Yes, so it gets puffed up. And that's when most of the time, if you have a some kind of screw or something that is holding the battery pack together, that puffed up thing might just get punctured. And if it gets punctured, that's when it can start burning, because it now has access to oxygen.
Oh yes.
So that's the way. Basically, that's why those gases are like in puffed up cells are called bad. You can recover those puffed up cells if you do not puncture the cell. You just
by doing what?
By charge cycling.
You mean doing the same thing that actually made it?
No, charge cycling, but not that entire like 10% to 90%, like 0% to 100%. Okay. Basically, charge cycle it from like 30% to 70%, 30%. Okay. If you do that multiple times, what happens is during that period, so it's like acid and base reaction. They basically exchange partners, right? And in one of the forms, that exchange partners like the result is a gas. Now it's outside of the system, still around the system but outside the system. The more you like do the exchange, more it has the reason to basically again exchange the partners again and not be gas anymore.
Okay, getting used up
and become part of the system. It might even like I have used a lot of cells like that, like really puffed up cells, and recovered them back from being puffed up to not puffed up anymore without puncturing or anything, just by power cycling it, because now those molecules are basically absorbed again as the like capacity of the cell. That happens usually when you keep a charged cell like 4.2 4.1 volt charged cell and leave it out for a long period of time. What is basically happening is that the internal resistance, no matter what the battery is, there's an internal resistance. Even if you're not connecting it with something, internally battery is very slowly discharging by itself. Previous lead acid cells and all used to be very bad at that, poor at that. They would just, if you leave them like that for 7 days, you can go and measure them, like really low.
And also there is some kind of rust happens.
Yeah, those kind of things happens. So that rust happening, how is it happening? Basically it's exchanging partners. That's the thing. Rust is like usually if it's a copper head, you'll see like something green.
Yes.
So yeah, copper carbonate, copper sulfate, those kind of things that usually end up happening. But in this case, that process is really slow. It ends up corroding the one of the like gates. I think it's anode, and it ends up becoming that gas.
Okay.
And because it's now a gas, and there's no good way to deposit it, the only way to basically pull it in, pull the part of the gas in, is by creating the voltage difference, basically sinking and sourcing, so that it basically finds, or whatever is that side that anode finds reason to basically get attached to that anode and then stay there. If you leave a highly charged cell for a long period of time, it will basically puff up. If you're trying to store the battery cells, store it under 3.6 volt, like these cells, 3.2 volt or something.
So you have to discharge and then.
Yeah. Right. All right.
How do you charge and discharge a naked cell like this? I mean.
Yeah, you can use the alligator clip.
Okay.
From the charging thing. Like I can show it here. Okay, wait. Let's go back to the thing. So you can have alligator clips that holds here,
Okay.
and you can apply charge from your whatever lab bench power supply you want to handle with care. So you can do that and it will charge. One thing about battery charging is that it's not that you just add plus and minus to two ends and it will charge. It's not that. You have to maintain the voltage to a certain degree, and more importantly, when it's discharged, you have to manage the current to a very certain degree. For example, usually cells are rated for 1C charging. Like you can go up to 1C. 1C means that rating that we saw, 3910.
Yes. Mm-hmm.
So 3.9 amps of current is 1C, its capacity, one current. Like one capacity. C is not really complex. This is a mechanic term. This is not a engineering or academic term.
I have heard this 1C to C.
Yeah, so this is the mechanic
big batteries that is used for inverter.
Yeah, so those will discharge at like even 50C, 100C even. Like they have very high discharge. Even these things have very high discharge, but while charging you need to slow charge. If you fast charge, the forming of hills are very likely. It's more likely. So you need to do slow charging. So when you are doing that slow charging, first you need to manage the voltage towards some certain level. It should not go above 4 volt, 4.1 volt. But more importantly, it should not even go more than a certain that current range. If you need to reduce the voltage to have that current range, you do that. So that's why Hey Saurav, na ami live chilam ami so we came live at 5-10 minutes later than usual. Sorry about that. It took a little while to set things up, and also basically bring up the stuff that we needed for making sure that even if the batteries catch fire or anything, we'll still be able to handle it. We actually went through the whole process. I hope that you watch the videos and you can go back and watch the whole thing. You will see. You can basically skip over if you want. But we went through the whole thing and we are now answering some of the questions that Preetham asked, Dark Rift asked, and Mumita is asking. So the question you asked is, what was that last one?
1C to C50C.
Right. So 1C would be rated as whatever the milliamp hour is written.
Okay.
You turn it into amp and use that. So 3910 milliamp hour is 3.91 amp hour. It's like
by
1000, so 1000 times more. So 3.9 amps would be the charging capacity for this.
Okay.
Right? So if you're charging it with 3.9 amp, and now you're seeing that the voltage is so low, the voltage is going down to 3 volt. It's deep discharge, it's 2.8 volt or something. Now in order to bring it back up, you have to start with that. Like the voltage will actually go down. It will not be 4.1 volt, 4.2 volt. The voltage will go down. The current will be same. You want to make the current same, and you have to increase the voltage gradually so that it keeps on charging at a rate. You're basically inflating a balloon.
Yeah, I understand, but it's so hard to do that.
That's why the battery charging circuits. That's why the battery charging ICs.
Exactly.
Those TP45, 4056, those ICs, that is a very workhorse IC because of that. Because that small thing is doing a lot of heavy lifting.
You can make a device with that, and then that device will make sure the conversion and that thing is exactly the...
Yeah, it's making sure, given how much charge I'm dispersing, I'm set to only disperse 1 amp of current. Now this cell at this voltage is taking up more than 1 amp, so I need to reduce the voltage to balance up to the point when it reaches 1 amp, and then gradually increase up to the point. And when it will reach a point where then it will enter a constant voltage charging mode. At some point, it will no longer take the 3.9 amps of current as input anymore. But if you measure the end points, it will not be 4.2 volt yet or 4.1 volt yet. It will be like 3.98, almost 4 volt.
Okay.
But you still need to, if you want to top up. By the way, that's the better place to stop charging. That's the 80% I was talking about. That's when you ideally want to just, okay, I don't want to charge it anymore. You lose out on the 20% of capacity, but your battery's overall run time would increase, then the charging cycle would increase. So that's when you make it constant voltage, and the current will basically gradually taper down.
Okay.
To the point when usually these circuits do that when the charging current is 1/10 of that rated current that it was charging, it will just cut off that, okay, battery is charged. So those are the things that is happening in here, right, for all 4 of those. And the yellow thing is basically to make sure that it's insulated. It's kind of insulating compound, some kind of thing. I really like this BMS. Like, of all the BMSs I've seen, this is the best one so far. And these are the 4 MOSFETs.
Okay.
These are doing this switching. Yeah, nice circuit. I don't think I would be able to use it because this works with SM bus and the pin out is completely mangled. But I will keep this for sure because this is one of the reference design of a board that is really well made. I actually like it. Whoever, I don't know, like I'm not sure. I'm very sure that the Lenovo engineer who designed this is not gonna watch it. However, like in case ever they watch it, I really like this board. Yeah. I am not going into the details of why exactly I like this board, but there are a lot of things that I really find interesting. Cool. So that's it. So now we have 4 cells. This is where I'm gonna end the stream. I'm going to make sure to charge and discharge the cells properly, cycle and understand exactly their power, how much power they're holding, how much power they're capable of holding. They're not bad, they're good cells, so I'm expecting pretty good results. And once that is done, I will tap the cells in a way so that they don't accidentally get short circuited, wrap it with Kapton tape and store it until the time I need it to
use it again for our projects.
Right. So that's pretty much it. Thanks folks, thanks for watching. So there's one more last thing that I need to talk about, that is I needed to turn off all the videos, like the live videos VODs from the channel because it was negatively impacting the like YouTube channel's algorithm. It kind of shows everybody those live streams. People don't click them. Of course, I don't see, and there's no way to disable that. The settings is grayed out, so any published video, it is by default shown to subscribers, and that's bad. When is the next stream? Every Sunday, this
8:30.
Around 8:30 p.m. Indian Standard Time. That's when I stream. At least that's what I'm going for. I'm doing that for the last couple of weeks. I intend to keep that going. Thanks a lot for watching. So that's the reason I needed to take down the video. I am planning to make a community post every week. That's what I was thinking, that because I have no reason to basically make the video unwatchable for people who want to watch it. But because it's showing to thousands of people and not the videos, the actual videos that needs to be shown, so that is a very bad. খুব তাড়াতাড়ি যাচ্ছি এবার. Not really. I started at 8:30 something, so I intended to do that for 1.5 hours. My daughter is probably getting impatient out there. So yeah, gradually probably will increase the time, like how long do we stream. I'm basically getting accustomed to this. I'm not a streamer. I am not a on-screen persona. So I need help and support, even keep what I'm saying on track, right? So those things. So gradually, if I get better at it and start enjoying more, which I am enjoying very much, we'll probably increase the time and all. And thanks a lot for the support, guys. Like I'm seeing the faces multiple times now, recurring faces. That gives a lot of confidence, a lot of basically the enthusiasm to continue forward like that. This is a hobby so far, yeah, but I really enjoy this. So I will go ahead and make community post where the URL of this video will be posted, so that YouTube does not end up annoying everybody who doesn't want to watch it. Exactly. And instead
whoever is interested.
It shows the videos. Also, it shows the videos that are actually made for showing to the subscribers. That's the way. So if you feel like you need to go watch the video, wait for the community post where I will be posting the URL. Click there, you'll find it. This is gonna happen from this week. Cheers and